let me start. So today we start really by studying general manifolds, okay? So in some sense, surfaces are over. So in fact, but then I immediately contradict myself. I want to make one example which is intermediate between the theory of surfaces we have developed up to now and manifolds. What do I mean by that? I think I made already some comments about the fact that now we are ready to understand the conceptual step of taking an object and freeing ourselves from the constraint of having to put the first fundamental form to be the one induced by the ambient space. Remember, up to now, what we have done was really to take a subset of R3, and then the main imposition we put was to always look at the scalar product between tangent vectors as the one coming from R3. Okay? And then we studied, okay, which curvatures depend only on the first fundamental form, which was intrinsic, extrinsic, and so on. Now, this is the conceptual step we have to make now in the final part of the course, getting free from this. I mean, when we say the first fundamental form is a symmetric positive definite operator given in local coordinates by some functions E, F, and G, then actually the reason, I mean, there was in principle, now you should realize that there's absolutely no reason why this is actually the one coming from the scalar product of R3. Okay? In principle, now every time you give me three functions, E, F, and G, in such a way that the matrix is positive, definite, and symmetric. Right? Symmetric you impose it just by brute force. It's E, F, F, G. Okay? But the positive definiteness, of course, it's a condition. Then you can actually develop the whole theory we have done using this as the first fundamental form, even if this matrix does not come from the ambient space. Okay? Now, in order to appreciate a little bit this step, let's make an example. I mean, this is just a reminder of the two things we are going to use later, I mean, the formula. In local coordinates, this was one of the simplification of the formula obtained by the Theorem egregium in local coordinates. And this is the system of geodesic equations for, again, for a curve parameterized by arc length and contained in a chart. Now, look at the following. In fact, I mean, with no mystery, a good, also historically, the example that connects the theory of surfaces in R3 and the theory of differentiable manifold anywhere is the hyperbolic plane, which is the following. I mean, it can be described in many ways. So the simplest, well, not the simplest. There are two very simple ways to describe it. So as a set, I'm really just taking the unit disk. So in R2, so what people say is that there are many models for this thing, okay, that you will call the hyperbolic plane, and then you have to tell explicitly what do you mean by that. So you take in the UV plane the set of points which are of norm less than 1. But then I define, of course, this I can think of it as a piece of a surface if you want, because it's a piece of a plane. No? But then I impose it, the first fundamental form I want to look at is not the one given by the plane. That would be E equal to 1, F equal to 0, G equal to 1. I want to impose the first fundamental form given in this form. And actually, let me explain. It's a notation, but actually it's a useful notation, and then in 2 or 3 lectures you will also understand why it's formally correct. It's 4 divided by 1 minus u squared minus v squared times du or du squared. Sometimes it's written dv. Okay. What does it mean actually, this notation? This is the first time you see it. So what it really means is just that E is equal to the coefficient of du squared. Why it's, how do you remember this notation? Because what is capital E? Capital E is the norm squared of the vector xu. Okay, if it, whatever, okay. So it really, what you should think of is that you take this as an operator on the quadratic form on the tangent space. So if I take dxu, so xu really I'm thinking of xu as the vector du, the partial derivative in the u direction. And then of course this symbol means it's the dual, it's the linear map which takes this vector and gives me 1 and takes the other vector, because then the tangent space would be generated by xu and xv. So xu, this takes xu, this vector gives me 1, and this takes this vector and gives me 0. So it's the dual element in the dual space to the tangent space to this thing. Okay? So you see, this object here means I take, if I apply this quadratic form to du, I get, well now, this is a little bit, because it has the same coefficient everywhere, but I get this function here. Okay, so du kills this and gives me 1, du takes this and gives me 1, and I'm left with this coefficient. Okay, so this would mean that E is equal to 4 divided by 1 minus u squared minus v squared. F is equal to what? 0. There is no du dv, no? Because, okay, F is equal to 0, and G is equal actually to the same thing, but for the opposite reason, for the other reason, because that would be this object here, which goes and takes twice xv. So, okay, so this is a very convenient way to write down quadratic forms, okay? Nothing more than that. I mean, there is no conceptual thing at the moment. I mean, we will see that there is actually a little conceptual content to that, but it will come later. Okay, so now this is the game I was telling you. I've given you 3 functions. Of course, in such a way, the matrix I build is positive definite. On my domain D, this is positive definite. First of all, it's well defined. I mean, this denominator, of course, that's why I'm restricted to the unit disk, to the inside of the unit disk. So it's in this way the functions are well defined, okay, and they are positive, okay. Okay, so I want to treat this as if it was a surface in R3, okay. What do I mean I want to treat it? I want to study its geometry exactly as if this was a subset of R3 the way we did. Now, of course, I cannot do everything. We distinguish between intrinsic and extrinsic. Of course, all the extrinsic part of the story will not apply because I don't have a normal vector. I mean, this is not sitting in R3, so I don't know how to choose n and then all the things that we build with that. For example, it would make absolutely no sense to compute the mean curvature. Okay? What I can do is all the intrinsic geometry. So, for example, it makes perfectly sense to study the Gauss curvature of this object by taking now as definition of Gauss curvature the formula that Gauss produced in the proof of the Theorem Egregio. Okay? And that's why I remembered here. So this, for example, is a case where f is equal to 0, so instead of taking the big formula, you can take it. So, for example, how much is k? So this object, this is a surface, in the sense that it is a 2-dimensional object. In some sense, it's even covered by one single chart. Okay, there is no problem of changing charts here, because it's one disk. Okay? So how much is k? Well, that would be minus okay. E and G are equal. Okay. So this, of course, becomes 1 over the square root of this function. So twice.
So can be E over 2.
Sorry?
Can be E.
That's 1 minus v squared minus v squared over 4.
Over 2. No, I have to take the square root.
Also, or is
no, because it's 12. Okay, so it's. Okay? And that's this one. And then we start doing the computations. Let's hope it works. So, this is du of what? Of 2 Okay, d is equal to this.
1 minus
So square root of g,
minus
so
v
it's
squared
2. Okay, and we agree that this is the square root of this function, and then times du of the same thing.
du over 2 over, no, the reciprocal of that.
Sorry?
The reciprocal of this, because it's square root of g, not 1
Can
minus
be
square root of g.
minus 1/2.
It's minus 1/2. Okay? Plus, and then of course everything is very symmetric in UMV, so then just by replacing UMV you do the same computation, dV times 1 minus u squared minus v squared, 1/2 divided by 2 dV of 1 minus u squared minus v squared minus 1/2 over 2.
Not over 2, I think. 2 times.
It's 2
It's
times.
2 times. In this, when we put the minus 1/2 before.
It's twice, yes. Okay. Okay. Now I don't do it. You do it in 5 minutes, and then this has to give you this. Okay. So everything has to cancel. So this is actually a model of geometry of constant negative curvature. Remember that in R3, as a surface of R3, the only model we had like this was the pseudosphere. Okay, so note that these are even topologically different. I mean, so this is not a chart of a pseudosphere or whatever. It's another thing. Okay, then another model comes from the following game. So now instead of taking the unit disk with this first fundamental form, one can take what is usually called H, which is just the upper half plane. It's the set of U and V, or actually maybe it's better to call them X and Y, so that in R3, in R2, such that Y is positive. So you're really just taking the upper half of a plane. Okay, now that's the other famous model for this space. And now I declare the first fundamental form to be just 1 over y squared dx squared plus dy squared. Okay, so this means what? This means that E is equal to G is equal to 1 over y squared, and F is equal to 0. So again, you fall into this category, F equal to 0. You can compute the Gauss curvature. And again, now I don't even write what you should do. In fact, this is simpler. Okay, because actually this is a function only of one variable. So this would actually disappear immediately. You are left with the second variable. Okay, this takes a few seconds. Okay, so this is called the disk model, of course, and this is called the upper half plane model. Okay, and now I finish the blackboard.
Can I ask something?
Yes.
Because there is a Möbius transformation into the half plane into the disk. So is there any relation
Exactly.
between?
That's the point. That's the point. In fact, these are not two different things. They are the same. Let me show you why, if I find a way. Well, okay, I will rewrite the geodesic equation in 10 minutes, okay? So let's first see that actually these are the same thing. By the same thing, I really mean there is an isometry between these two. Actually, since you seem to be quite receptive to this strange notation, let me make one step forward, because in this game, as your colleague was saying, you start feeling the smell of a Möbius transformation. So complex coordinates are very useful. Okay, so if we start using complex coordinate, here I would call a complex, in the model 1, I would call the coordinate z to be u plus I v. Okay? And if I do that, actually the expression for the first fundamental form becomes much more elegant. Well, not that it was too bad, but I mean, it's even more elegant because it becomes just 4 divided by 1 minus the norm of z squared, because of course u squared plus v squared is the norm of z. Oh, and then actually it would have been nice to write it down correctly. Sorry. This is squared, which actually would simplify, forget all this. Okay? I forgot the square, which kind of is important, of course. So you have to replace everything by the square, so that these 1/2 are not there. Okay. In any case, so this is 1 minus z squared, and then actually this operator du squared plus dv squared, you can check immediately that this just becomes dz bar formally. Okay? Now for you this is just a game of symbols, okay? Because what do I mean by dz? If z is equal to u plus iv, I really mean dz is the complex operator which gives du plus I dv. So I'm thinking this now acting on complex vectors. Okay? So the tangent space, and then dz bar, of course, if z bar is u minus iv, dz bar is just du minus I dv. Okay? Now if you formally do this product, you get that this is equal to the u squared plus dv squared. Okay. While in the second model, if I call w the complex coordinate x plus iy, then the first fundamental form becomes just, well, y is just the imaginary part of w, so I cannot simplify that. This just becomes 1 over imaginary part of w squared, and then again the x squared plus the y squared is the w bar. Okay. And this is just a convenient reformulation, because once we put complex analysis into the game, how do we do it? So the first claim is that 1 is isometric to 2. Okay. So what do we need to construct? We need to construct a map phi from D to H, for example, which sends the first fundamental form into the first fundamental form. And this can be done in this way. So of course this will take z into something, into w, but w of the form I 1 minus z 1 plus z. Which actually, it's also nice to write down the inverse. So that's the Möbius transformation you had in mind. So z is actually equal to I minus w, I plus w. Okay. This you have studied in complex analysis because it's the famous way. So you decide what is the point at infinity, which I think in this point here, and then you're just opening up the disk, okay, with a holomorphic map. Okay. So this is a Möbius transformation, and then my suggestion how to do this exercise is what? Is how? For example, write down. Well, this is a bit. It's the same. It contains the same level of complication on both sides. So, of course, you take formally dz, and you take dz, but z is equal to this, and you express it as a function of w. Okay. So, for example, what do you get here? You take dz becomes, of course, the derivative of this with respect to w. I mean, you are treating complex coordinates as if they were normal coordinates, okay? So, by chain rule, you take this function, you take the derivative with respect to w times dw. Okay, so what is the derivative of this with respect to w? Well, this becomes, of course, 1 plus w squared, okay? And then if you do the computation above, you just get minus 2I dw, okay? And of course, if this is z, of course, z bar would be the bar. So if I want to use the complex version, I need to compute dz and dz bar. So that's dz bar. I do the same, and I get that dz bar is equal, of course, just twice I dw bar, and then it's just divided by, oh sorry, this is an I, yeah? Divided by minus I plus w bar squared. Okay? It's just immediate. Of course, this becomes minus I plus w bar, no? So, okay, so then you plug everything there. So you take this formula, for example, for the first fundamental form on the disk. Now you can replace dz bar by this formula, and you know what is z as a function of w. So you make all the big change, and then, of course, what you get is that one. Okay. So this gives now. So that this tells me that the first fundamental form on the disk is actually equal via phi to the first fundamental form on the hyperbolic, on the upper half plane. Okay, it's a straightforward computation. Okay, so these are actually the same surfaces with fundamental form. They are not just homeomorphic, diffeomorphic, but there is something more on that, no? In fact, okay. Okay, now, this is actually what I wanted to tell you conceptually, but now the classical exercise on the hyperbolic plane is actually to compute the geodesics. I mean, what are the two things which we know for sure they are intrinsic? Curvature, Gauss curvature, and geodesics. Okay, so we cannot do much more. I mean, well, we know the area of domains, the length of curves. I mean, we know many things, but for sure, we know geodesics and Gauss curvature. So the Gauss curvature is constantly negative. So how do we compute geodesic? Well,
I just have a question regarding this differentiation. How did we do it formally with respect to the W bar?
well, Z bar is minus I minus W bar. It's a parameter, no? W bar. So you take the derivative with respect to W bar, and you have an expression which depends on W bar. So you take the derivative. Now, okay, let me reorganize the blackboard. We will not discuss the geodesic equation in the disk model, but we will do it in the upper half plane model. So let me cancel this thing, and let me save. Well, of course, everything now we discover on the upper half plane can be translated into the disk via this map. Okay, so even this one, we don't need it. So, okay, let me rewrite here the system. D in dt of E u dot plus F v dot is equal to 1/2 EU dot squared plus 2F u dot v dot Fu u dot v dot plus Gu u dot squared. And then we have D in dt of F u dot plus G v dot 1/2 EV u dot squared plus 2FV u dot v dot plus GV v dot squared. Okay, so this is the system of, and this is our model. Okay. Okay, so what we need to compute, I mean, this is a bit easier. So now remember that in this language, x is equal to u and y is equal to v. Now we have to order which is the first coordinate and the second coordinate. X would be the first and y would be the second. And then in this language, of course, E, we decided that E is equal to 1 over V squared, and F is equal to 0, and G is equal to 1 over V squared. Okay, so we can do all the computations we need to write down the... So how much is EU? Well, so let's write down everything. So we have, except F, of course, we don't care, because it's 0. Then how much is EU? Well, EU is equal to GU and is equal to 0. You see, this is a very nice accident. And then what? EV, again, is actually equal to GV. Okay, and is equal to what? Well, this is V to the minus 2, so it's minus 2, so this is equal to GV, is equal to minus 2 over V cubed. Okay? Okay, so let's write the first equation. Let's call it number 1 and number 2. So number 1 becomes what? So this is d in dt of 1 over v squared u dot is equal to 0. And number 2 is d in dt of 1 over v squared v dot is equal to what? Is equal to minus, the 2 kills the 1/2, so this is minus 1 over v cube. Well, the 1 over v cube I can put it outside because it's both here and here, and then I'm left with u dot squared plus v dot squared. Okay. Okay, so this is the system of equations we want to attack, but remember this applies only to curves which are parameterized by arc length, and we have already seen examples that actually this is another equation that turns out to be always very useful. Okay, so there is a hidden equation here involving E, U dot, F, G, and V dot. So, but remember, so of course, what does it mean that it's parameterized by arc and that the tangent vector to the curve gamma is of norm 1. But norm with respect to this way of measuring norms. Okay? Not Euclidean. So again, the fact that the norm of gamma dot of S of t actually, in my language now it's t, is equal to 1, but this norm is this one, so that actually this becomes what? This is, by definition, it's EU dot squared plus twice FU dot V dot plus GV dot squared. Okay, that's what it means to use the first fundamental form to compute the length. So again, of course, here we have this, and here we know what it is, because E is equal to 1 over V squared, so this is 1 over V squared times U dot squared plus V dot squared. Okay, so in fact you see, so this equal to 1, this is the real equation, no? This is the extra equation we have. Okay, so and now I'm going to leave you most of it as an exercise, but how you do it. I mean, you manipulate these equations in nice ways, but in some sense you need to know where you are going, because this becomes a very hard system of equations if you just don't know where to look. One thing you can easily observe is that first type of examples you take, I mean, natural thing to do are segments. I mean, after all, I'm taking a piece of a plane. Now the point is that I'm distorting the plane in the scalar product, but in some sense it would be natural to start checking, Are straight lines geodesics? Okay. Well, and actually you can see that the answer is no, unless if you take u is equal to a constant. So what does that mean geometrically to take u equal to a constant? U is equal to x. So you are taking vertical lines. Okay, so this is u equal to u naught. And this is u naught, of course. Then you see that this equation here, which is in some sense, it's the bad one. Well, or this disappears, no? Because u naught becomes 0, so this becomes automatically true. And then the other one, it has been completely decoupled because u dot is disappearing. And then you are left with an equation on v. V, of course, I'm thinking of v as a function of t. I mean, gamma of t is now written as u of t, v of t. Okay? So these are all functions of t. Okay, but even if you expand it, doesn't matter, because remember, d in dt will act on this coefficient, okay? So this will become 1 over v squared v double dot plus the derivative of this with respect to t times v dot. And then you have to cancel something, you have to use this one to simplify a little bit. But whatever, it's just an equation of the function v, okay? But it's easy to see that it has a solution. The point is that this is not, for example, just check this. You might think, if it's a straight line, maybe it's a straight line also parameterized in a natural way. What is a natural way to parameterize a straight line is to take v of t equals something of the form at plus b. No? Kind of a uniform motion on this straight line. Would that be nice for this equation or not? Well, of course, this makes v dot equal to a constant.
Can't we
Yes,
decouple
it
it
is true.
from the beginning instead of...
Sorry?
Can we decouple it from the beginning because we can make this right-hand side minus 1 over v? I mean, we get to separate the differential equations.
I don't think you can actually decouple it in general.
Because here we have some conditions that 1 equals 1 over v squared, blah, blah, blah. So at the second equation, we can write it minus 1 over v squared.
Yes, in this way, yes, you can. Well, not completely, no? Anyway, don't worry for a moment. I mean, you will see that the linear parameterization of a line doesn't work. Okay? Well, it does not satisfy this, for example. Because this is 0, this is a constant, and this is 1 over a linear function. And this should be equal to 1. Okay? So this is not a solution that you can accept. But still, there will be a solution. What does it mean that geometrically there is a solution? That it's okay. There is a function v of t in such a way that if I take u naught, comma, v of t is a geodesic. Okay? But it's not going to be this one, contrary to the Euclidean situation. Okay? But in any case, the geometric statement is correct. Vertical lines are geodesics. But that, you just have to remember that you need to parameterize them in a strange way. Okay? For example, you can actually check that in this parameterization, t has to go to infinity when you reach the boundary of the upper half plane. Okay? That's one property you can check out of the... And I don't suggest you write down the actual solution. You just study the properties. Okay, then I'm just telling you the output. You can play with it just to see whether you can prove it, because then the other source, and remember, this is a situation where it's very important to remember the statement about existence and uniqueness of geodesics. Okay? in the sense that the second guess you can make is the following. You take pieces of course, the upper half part of circles where the center is on the missing horizontal line. Okay? So, now, if you do that, this is a much more elaborated thing, because now in this case, you see this problem of the strange function in which you parameterize the curve. So here, how would you would be tempted to parameterize by sine and cos. Okay, depending of course on the center and the radius, but I mean, as you do in the Euclidean case. But then again, this would be very far away from the actual arc length parameterization with respect to this. So here really you have to work with these two functions u and v without actually knowing them. Okay. But in any case, this will give you solutions, and then the final step is to realize that these are enough. There can't be any, so geometrically you guess these two things, you check, and then you say, well, but now I remember the theorem which tells me that for every point and every vector here, tangent vector, of course, the tangent space would be the space itself, because I'm taking a piece of a plane, okay? There has to be one and only one. And now, a little bit of geometry. Are these enough? Well, if the vector is vertical, I have the vertical line. If the vector is not vertical, well, I told you this again, you can actually find only one circle with center on the horizontal line, y equal to 0, passing through this point with this tangent vector. Okay? So these two objects cover all possibilities. There can't be anything else. Okay? So it's quite curious, no? I mean, it's a kind of a strange geometry. So for example, historically, which was the most surprising property of this? It's actually, I mean, this is just an historical comment, but this showed once forever, if there were any more doubts, that the fifth postulate in Euclidean geometry is not a theorem, it's a postulate. Remember what does the fifth postulate say? I mean, for 2,000 years, people have been asking whether Euclid was made a mistake. So when you postulate something, of course, elegance in logic imposes you that this should not be a consequence of the previous postulates. Okay? Otherwise, it's not a postulate, it's a theorem. So the fifth postulate is the most famous of Euclidean geometry because of all this history. And it was asking in Euclidean space, if you give me a line and the point outside, it was postulating there was one and only one parallel line. Okay? There exists one and only one parallel line to the given line passing to the given point. Okay? So this Euclid put as a postulate is number 5, and since then people have been asking whether you could actually prove it using the others. Okay? It's a beautiful story again, but I don't want, this is not a course of history of mathematics. I mean, people have tried to prove it. There are books and books and books of people trying to prove it. Of course, many people claim to have proved it. The most famous one is an Italian priest called Girolamo Saccheri. I don't know how to say it in English. It's Euclides Vindicatus means kind of Euclid, the title is Euclid kind of cleaned up or restored of his dignity, because of course for a mathematician to put a postulate which is not a postulate is a mistake. No? So he was claiming actually to have proved it. Well, okay, now 3 minutes of break of his history. It's actually a beautiful book. It has been very important because he actually wrote a whole book about trying to prove this postulate. And basically what he did, historically it's very important, this book. Mistakes are important in the history of mathematics, because actually, basically he wrote the first book on hyperbolic geometry without realizing. And then at one point, he translated the postulate in many equivalent ways. And at one point, he found one property of parallelograms, hyperbolic parallelograms, which was so strange that the book finishes by the famous sentence, and this violates the nature of a line. This has become a very famous sentence in mathematics, because of course it means nothing. Okay, what does it mean? What is the nature of a line? I mean, you define what is a line, or you assume it as an intuitive concept at the beginning, and then there is no nature, okay? So what he didn't realize is actually that this sentence doesn't make any sense, and he actually produced the first book of hyperbolic geometry, really, okay? Now, why? Because let's go back to the hyperbolic plane. What's happening about on the fifth postulate here? Now, of course, you are replacing, in all this game, you replace the word line with the word geodesic. I mean, what is a line on a space which has no, okay. So a line is, in some sense, the curve of shortest length joining two points. Okay, so you take this and then you extend it to the notion of geodesic. So what's happening to this famous fifth postulate here? If you take a geodesic, now you know exactly which are the geodesics. If you take a geodesic and a point outside, does there exist, and how many, geodesic, lines passing through this point? And what does it mean parallel? But parallel means just they are not intersecting. Infinitely many. Okay? So that's one way to violate the fifth postulate, because of course you could violate it the other way. There could be none. Euclid is saying there is one and only one. So you can violate it in two ways. There is none, or there are more than one. So this is a situation where, of course, there are infinitely many. Okay? Of course, plus this. There are infinitely many. So this actually, the existence of the model of hyperbolic geometry closed this 2,000-year-old story forever, because, of course, the problem is, if you remove the fifth postulate, do you end up with a system of postulates, axioms, which are logically consistent? Yes. It's this geometry. Actually the existence of the model proves it's consistent. It exists. It's there. I wrote it. Okay? So if you want to do Euclidean geometry, you have to put the fifth postulate, but you are allowed not to put it. That's the point. And you are perfectly logically okay. You are doing something else. Okay? For example, you can do hyperbolic geometry. So that was really the end of Euclidean geometry as the only geometry. Okay? Okay, so these are a little bit of history and final game. And you see why this is an intermediate thing between surfaces in R3 and completely abstract objects. Because of course this is still a two-dimensional object. But now, in fact, you could ask the question, is this isometric to a surface in R3? Maybe I wrote this first fundamental form in this way just by elegance. But maybe there is a surface in R3 which is actually diffeomorphic to this set, and actually has the first fundamental form coming from R3, which under this diffeomorphism becomes this one. So there is still one important thing to know about this model. Is it a surface in R3 just written in a mysterious way or not? Well, in some sense you can take the classification theorem of surfaces of constant curvature we proved, okay, because we know that it's not a pseudosphere. Or you can actually try to push this into the Euclidean space itself and see that it doesn't work. Okay, there is no isometric embedding of this object into R3. Okay, so this is genuine. Okay, so now we are ready. So that's it. Surfaces from now on will be used just as a source of inspiration for general geometry. Oh, just because you can actually, if you get, I mean, it's easy to get a little bit passionate about this this geometry. You know, it's very prestigious. So once you know what is a geodesic, in some sense, you are using the word geodesic thinking of lines in Euclidean geometry. So for example, you can draw polygons. No, I mean, just the edges will be pieces of geodesics. Okay, so for example, you can draw triangles. For example. So if you want to know another quite unbelievable, this is of the type of the things that Saccheri consider violating the nature of. Okay, so you can actually play this game if you want. It's a beautiful game. Draw a hyperbolic triangle. Now you know how are the edges. No, the edges are this kind of pieces of circles. No, so for example, an hyperbolic triangle will look, for example, like this. Okay? The edges are geodesics. Now, it's slightly more complicated, but not much of what we did up to now. You can actually compute the angles at the edges, which are made by the edges. Okay? What does it mean? You compute these vectors and you use the first fundamental form, no, by the usual Schwarz formula, no. So, for example, one nice game that you can play is how much is the sum of the angles of the interior angles of a triangle in hyperbolic geometry. Because remember, probably the most famous theorem in Euclidean geometry is that this should be pi. Okay, so how much is it in the hyperbolic space? How much? But that's the point. I mean, there is no formula. I mean, there is no number answering this
But I
question.
think that's
It's less than pi.
As smaller the triangle, much more accurate, much more near to pi. Or
The smaller the triangle, but again, even smaller, it's now a new word, no? So in fact, I didn't want to spoil you the surprise, but I mean, the point is that below pi, anything can happen. That's the point. For example, think of this monster. Batman, a half Batman, no? But this is a triangle. But, well, it's a limit of triangle, because now remember that these points are actually not there. So the vertices, I threw the vertices at infinity. Okay? Because this really becomes an infinity, metrically speaking. In terms of distances, this line here is a distance infinity from here. Okay? But somehow, what I do is kind of certainly a limit of things. I could put the vertices at height epsilon and then let epsilon go into 0. Okay? Well, but now how much is the angle? 0. In fact, you can even get as close as you want to 0. Oh, okay. So there is no formula. I mean, from pi to 0, you can get anything you want, provided you construct the right triangle. Then again, it was another quite amazing intuition of Gauss and Bonnet, actually, in this form. Probably the most famous theorem of this type is the Gauss-Bonnet theorem, which relates, in fact, the defect from pi in terms of the area and the Gauss curvature of the surface. So there's a formula which actually, there is a way to answer this question, but you need to tell me the Gauss curvature, the area, and then I can tell you which is the sum of the interior angles of a triangle. Okay? And we didn't know for more than 2,000 years this formula, just because this formula has a k, which in the Euclidean geometry is 0. So this formula gives you always pi, independently of areas and so on, when you do Euclidean geometry. Okay? Final remark. Now, definition of a manifold, otherwise we will never start. Okay, the definition of a manifold is just the usual game, mathematical game. No? We take a key property we found in the case of surfaces and we put it as a definition. So, remember, I cannot just take the definition of a surface, because that was actually embedding something into Euclidean space. That's precisely what I don't want to do. But if you remember, so now the critical picture is, of course, now pictures stop being meaningful. These are just helping intuition, but I mean, when I draw something like this, I don't mean something inside R3. Okay? So this is, suppose I have a set. But remember what happened in the case of surfaces. If you had two charts overlapping, so this is the key property you have to have in mind. Now let me call it x alpha, x beta. I think we were calling them x and y when we did it, but I mean now I want to have freedom to have as many as I want. From some domains of R2, u alpha and u beta, if they were overlapping, there was some kind of transition area, which corresponded, of course, to something on the corresponding domains. And we observed, we used it actually many times, which property? That if I now go from here to here, by composing with the inverse of the second map, okay, the definition of charts was giving me for free the fact that this map restricted to the gray area is a diffeomorphism. Okay? The change of chart property. Now you see, I cannot go there now anymore because that would be a map in R3 and I don't have R3, but I can still speak of this on an abstract space. And that's exactly what I want to do. So definition. A differentiable manifold is what? Well, actually of dimension n, this is useful for, to fix the dimension once forever. Okay, is what? Is a set M and a family of injective maps we call x alpha from u alpha to m, where u alpha is an open subset of Rn, and properties. One, well, first of all, everything has to be touched. So remember, for any p there is something. Okay, so that means if I take the union over alpha, this, of course, here I'm thinking it's a collection, it's a family parameterized by some alpha in some set of indices. Okay, countable, finite, more than countable, I don't know. Okay, but x alpha varies in some set of indices, let me call it capital A. So if I put them all together, I need to have everything. That's for sure. And now the critical property, anytime for any alpha and beta, for any pair of indices, such that the two things intersect, x alpha of u alpha intersection x beta of u beta is different from the empty set. In fact, let me call, before saying it's different from the empty set, let me give it a name. Okay? It's the gray area, no? It's the gray area here. Okay? Every time I have something like this, x alpha inverse of w and x beta, I can do x alpha and x beta inverse because that's part of w, are open. And x beta inverse composed x alpha are sin phi. Okay? Please note one thing. M is not even a topological space. M is a set. Okay? So I cannot say x alpha of u alpha is an open set. Doesn't mean anything yet. Okay? I'm putting a differentiable structure on something that a priori is not even a topological space.
But can't we naturally induce a topology using
Wait,
this one?
I mean, in 1 hour, yes. Okay? But then, okay, this is the key property. Then actually there's a slightly mysterious property. We will come to that on the examples. I mean, the comments on this. So the family u alpha x alpha, because now really what makes everything a manifold is this space, no? Is the choice of these open sets of Rn and maps. Okay, so if I look at the whole family, so I claim that I want that this family is maximal with respect to the previous properties. Okay, so what does it mean? A family is maximal with respect to property that if there was another one, V and Y, such that if I take this family, but there is a V and Y, such that if I put V and Y into this family, 1 and 2 still holds, then V and Y had to be one of them. Meaning, if it's not true, you add it. So in fact, once you have something which satisfies all these properties up to here, you can actually maximize your family. So suppose you have a family which satisfies everything, but you still don't know it's the maximal. Well, don't worry. You can actually say, okay, now I take the maximal family satisfying this. Okay. Okay, in fact, let me contradict already myself. Why you have to put something like this into the game? Because, for example, okay, what is, for example, a differentiable structure on Rn? Okay, let's do the trivial case so that you understand that there is a little subtlety. So, if I take Rn in the way I always thought of Rn, with its Euclidean topology, with the usual notion of differentiable functions and so on, what am I really doing? Well, I take it as a set. I would be very tempted to take U1, so A to be formed only of one index, U1 to be Rn itself, and X1 to be the identity. Okay? And then, is this true? Well, yes. Rn is open in Rn. it covers, I mean, everything it becomes trivial. Also because remember that anytime something you cannot check, it's true. So for example, in this case, property 2, it's uncheckable because I don't have, I have 2 indices, so it's true. Okay? So that gives me the standard differentiable. Is this a differentiable structure? Well, not really, because the differentiable structure is really the collection of these things. So if I say, well, Rn is a differentiable manifold because I'm thinking of Rn as Rn comma identity, then this would be different from, suppose now that you say, well, I always take Rn, the usual one. And now instead of taking one, I take, for example, all disks, all balls. I leave you free to choose the center and the radius with the identity. I mean, of course, I'm doing, again, the trivial thing, no? Then you say, okay, now there is something I need to check. Okay, the balls are open. The balls cover. Now, balls can intersect. But is this true? Yes, of course. I mean, in fact, the maps are the identities, so I mean, the identities are always, okay, take the intersection of 2 balls and the identity is a smooth map, okay? If there wasn't line 3, then you would have Rn with 1 chart. Let's start calling them charts, okay? And Rn with the collection of balls, they would be 2 different differentiable manifolds. Because the differentiable manifold is the collection of these things. And of course you don't want this. I mean, you know that these are the same. You are just describing them in a different way. Okay? So property 3 is there to kill this triviality. Because now if I start with Rn, with 1 chart, Rn, then this maximality property forces me, for example, to add the balls. So I cannot say I take Rn with 1 chart as a differentiable structure. Because if I take a ball, of course, the ball, I mean, this was true even with 1 chart. So if I add 1 ball, it's still true. And now if I take the change of chart between everything and the ball, of course, it's always the identity, so it's smooth. Okay? So it satisfies 1 and 2, so I have to add it. Okay? So for example, in this way, there is a unique differentiable structure on Rn that I can call the standard one. Otherwise, you like ellipsoids, he likes paraboloids, I mean, I like half planes, and then everybody has a different description of the same thing. And we will never be able to say that they are the same. Okay? So, in any case, I mean, this is psychologically annoying, but actually it's the most trivial thing to do, because, again, the procedure of adding, I mean, once you reach the level that you have described, property 1 and 2, you say, well, and now I take the maximal family. Okay, and of course I will never be able to write them down all. Okay. Okay. So this is a definition. Well, and then actually, let me answer the observation of your colleague before. I pointed you to the fact that this is still just a set. Okay. But actually, let's observe it immediately. M gets a topological structure automatically out of it. I mean, or else you can say a differentiable structure induces a topology. How? Well, to tell you which is the topology, I have to tell you what is an open set. Okay, so when is a subset? So we declare A, no, you know, I'm short of names. B, not great fantasy. So I take a subset, when I will declare a subset open, So B containing them is open if what? Well, of course, I will use these maps to bring back the topology of Rn, okay, at least on the part of B which is touched by this map. Okay, so if so remember the maps goes in this way. So now if I take a subset B here, what can I do? Well, I can look at the charts which are touching it. Every time a chart touches it, I go back to Rn. Okay? So I take x alpha inverse of B intersect x alpha u alpha. Okay? So do we agree that this is a good thing to do? I take the intersection with the chart and pull it back to Rn. And then if this is open, now Rn, of course, I'm treating Rn with a standard topology. I mean, this is a choice. You could disagree with that. But we are importing on a manifold somehow the local topology of Rn. Okay? So it's open anytime for any alpha. Well, I don't have to say for any alpha which touches B, because of course, if it doesn't touch, it's the empty set, it has to be there, okay? Now, it's very easy to see that this defines a topology. No? You have to prove that the union of open is open, and the finite intersection of open is open, and so on. The empty set is for sure there. Everything is there. The whole space is there, by definition. Okay? So this is one way to induce a topology over a differentiable manifold. Okay? Now, of course, why this should be a natural topology? Because, of course, with respect to this topology, which I will always refer to the induced topology, so for the induced topology, we are declaring these things open. So the charts will actually be open maps. Okay? I mean, this is the key property. And of course, with respect to this topology, all the maps involved in the construction of the charts is continuous, are continuous. Okay? So in this sense, this makes the whole structure topologically compatible. Okay? Okay, so I think we can stop here. There are some delicacies in, I mean, you can, depending on how much you like to think of. So for example, you might start wondering, was it necessary to fix n right from the beginning? Or does n come from somewhere hidden in the property? Again, the game like the fifth postulate. I mean, you want to give the minimal number of impositions and then to understand what is. So for example, that's a nice question to think a little bit about. I mean, can you leave, in principle you could have left n to be undecided, but then it would depend on alpha. Who knows? Maybe this would give a different definition of manifolds or not. Okay, so we will start seeing examples and the main properties next lecture.